Good morning, physics community. Today we're going to put into place a little more of the theory behind periodic motion, and that's going to set us up so that we can talk about waves, another important kind of motion. What I wanted to do first is to discuss the results of the pendulum project just a little bit. Then we're going to look at the physical mechanism that underlies repetitive motion, and it's surprisingly simple and common to many processes. And so after that, you'll work through your textbook, chapter 13.1 and 13.2, and we'll have a short Pearson quiz at the end. So let's get started. Now, as far as the project results went, they were pretty good. And insofar as you controlled for your variables, you got very good results. But there is a correct answer to the research question. So let's recall what that was. Which has a greater effect on the period of a pendulum, length or mass? And the answer is, the mass has no effect on the period of a pendulum at all. If you properly control for all the other variables, L, you have a good fixed point, you've reduced any kind of wobble, that kind of thing, then you would get no effect of mass on the period. Insofar as you didn't control for one of those, you might have gotten some ambiguous results. So let's just take a quick look at how that turned out. Now, one interesting result that we saw, and when you're plotting mass versus period, mass in kilograms, period in seconds. Some people got an ambiguous result like that, where the mass rose with one change the period rose with one change and then fell with the other change. And what one person did, and this is really interesting, they went back and they observed their pendulum and they saw that the pendulum pivot point was swinging a little bit, was moving a little bit as the pendulum swung. And so they went and controlled for that, stabilized their pivot point, and got perfect results, that there was no relation between mass and period. And what's going on there, and this is an interesting result, I hadn't actually thought of it, but what's going on there is if your pivot point is able to move, the more mass you have, the more motion you're going to get. And that's going to affect the period in complicated ways. Now, with length versus period, that's the length, the pivot point to the center of gravity of the mass, most people got something like this, right? Where clearly, as the length increases, the period also increases. So that's a direct relation. Length is proportional to period. But the actual proportionality turns out to be a little complicated. The real formula for the period of a pendulum is 2 pi square root of L over G. And you'll see that in your textbook today. But in any case, period varies not with the length, but with the square root of the length. And a lot of you got that little bit of a kick there, but you didn't have enough points to really pull that result out. And so one other point about the results that was, let's say, a point that you can improve on in the future is that 3 data points is the absolute bare C minimum number of points for a study. If you'd have gotten in a couple other points, maybe 5 points, you might have been able to pick up a little bit better idea of the best fit line using your R-squared value. But in any case, if you had this and you got that and you thought it was linear, that's fine. That's a decent guess at that point. So what we're going to do today now is we're going to look into why it is that this kind of periodic repetitive motion occurs. So let's start with the pendulum. And in a word, the reason why periodic motion occurs in nature is that there is an equilibrium to a system. That is to say, a state that the system seeks in which it is stable. Now, let's take a look at our pendulum. The equilibrium position for this pendulum is right like that. When that pendulum's just hanging there like that, all the forces are balanced, and in the absence of an unbalanced force, it won't move. What happens with periodic motion, then? Well, let's diagram this real quick. Okay, so what we're talking about here with a pendulum is we have an equilibrium point where all the forces are balanced. We have a force of gravity, and we have a tension force in the string. They're balanced, and it won't move without an unbalanced force. Now, what we can do, though, if we pull this away, when the pendulum gets up to here, suddenly we have an unbalanced force. And let's see where that comes from. So when we pull our pendulum out to here, we still have the same gravitational force. And we do have a tension force. But what's balancing that tension force is this component of gravity here. We'll call that FGY. There's another component of gravity here called FGX that is not balanced by anything. And what you can see is that that unbalanced component is going to tend to pull this back toward equilibrium. And then it'll have some kinetic energy at that point, and because it has inertia, it's going to overshoot that. It's going to go back up here. Then we have a similar situation. Now, the magic of this, though, is that as soon as it crosses the equilibrium point, that unbalanced component of gravity flips to the other direction. And again, pulls it back towards equilibrium. So that as this swings back and forth, as it passes equilibrium, this force, this unbalanced force, magically flips back toward equilibrium so that it continues to cycle like that, overshooting, being restored. We call that force there the restoring force. And all systems that are in harmonic or periodic motion have that. So we have an equilibrium, and when it's disturbed from equilibrium, we have a restoring force. And we have inertia that causes the system to overshoot the boundary. Right? It's driven back by the restoring force, hits equilibrium. It doesn't just stop there, it overshoots, and then it's driven back. And that's how periodic motion occurs. Now, let's look at that in a couple of other examples. For one, we could take a ruler, and I'm just going to sit on this. Okay, this ruler is in equilibrium. If I press it downwards, it's now out of equilibrium, and because of its elasticity, I've deformed it from its original position. It's going to have a restoring force. And when it snaps back because of its elasticity, it hits equilibrium and then overshoots. And then suddenly the restoring force is back towards equilibrium. And that's how you get that repetitive motion. Let's look at another simple example that you've experienced. Let's say you have a bowl or the bottom of a hill or something like that, and you have a ball. If you leave that ball go and just let it come to rest because of the damping effects, so friction, etc., it's going to seek this position here where it's in equilibrium, where the force of gravity is balanced by the normal force. if you pull that ball up here, then suddenly it's going to have a restoring force, a gravitational force that way, and it will roll back. And as soon as it passes equilibrium, that gravitational restoring force reverses direction, and you get harmonic motion again. Let's think of one more example. I want you to think about a bell, right? A bell, even though it's very hard, is an elastic object. So we have a bell right here, and it's got a certain shape. And if you deform the bell from that shape, by its elasticity, it's going to snap back. And when it hits its original shape, because it has inertia, it's going to overshoot, and it's going to start oscillating. And we can do that with the clapper. We can just hit it. But what we've done in that case is we've deformed the bell from its original position, and by its elasticity, it snaps back. And then by the logic of periodic motion, it overshoots its equilibrium and snaps back again. And we call that kind of periodic motion, where you have a single object is the system and its own elasticity is the restoring force, vibration. And vibration is the basis of most sound. So when we get to sound, we'll find that sound is almost always produced by something vibrating in response to a disturbing force. So the basics of periodic motion are: a system has equilibrium. When it's disturbed from that equilibrium, a restoring force tends to return it to equilibrium, but because of inertia, it overshoots. And if that is due to its own elasticity, we call that vibration. Now, let's think about one more example, a little bit more complicated. This is called a spring mass system, and we can think of this simply like as a trampoline. And let's say we have a person on the trampoline. They're going to depress the trampoline, right? Let's say this is its natural state. And the person standing on it is going to depress it slightly. And then that becomes equilibrium, where the force of gravity of the person is countered by the normal force of the trampoline surface, which is provided by the elasticity of the strings. Now, if that person instead jumped from up here, when they hit equilibrium, they would have a kinetic energy and they would overshoot. So a person bouncing on a trampoline is going to overshoot like this, which means this normal force provided by the springs is going to be greater than the force of gravity, and they will then accelerate upward. Okay, so that's the person up in the air now, right? And once they've done that, then there's nothing to balance the gravitational force, so they go past equilibrium, and then the gravitational force becomes the restoring force and pulls them back down. Then once they hit here, because they have kinetic energy, they're going to go past this equilibrium, and the spring force sends them up. So the restoring force in the upward direction is the spring force, and in the downward direction is gravitation. That's the basis of a bouncing ball and a number of other things. Now, the last thing we want to look at is, we'll talk about this a little more tomorrow, but most systems have what we call a natural frequency, and it's set by their physical parameters, right? So with a pendulum, the natural frequency equals 1 over the period, right? And we know that the period of a pendulum through experimentation, we figured this out, equals 2 pi square root of L over G. And that's set. It doesn't matter what the mass is. These are the only two factors that change that. Now let's take a look at units. We know that the unit for period has to be seconds, right? So the unit for this should be seconds. Let's work that out. So that's going to be L is in meters. So the units for this is square root of meters. G is in meters per second squared. Meters cancels out, seconds goes up here, take the square root, equals seconds. And that is the period of a pendulum. And you'll have to do simple problems working that out. Now let's take a look at one more. Another very controlled system is the spring mass system. Where you have some kind of a mass suspended from a spring or between two springs and it's free to oscillate. Now, again, the natural frequency of the spring mass system will be determined by it physically, and it equals 1 over the period. And the period of a spring mass system equals 2 pi times the square root of the mass divided by the spring constant k. And notice this 2 pi is telling you that these are sine wave motions. And if you look in your book, they have a very good explanation of this. Now, as far as units, this also has to be seconds. So the units are going to be the square root of kilograms over newtons per meter, which is going to equal the square root of kilogram, multiplying both by meter, kilogram meters over a newton. But we know that a newton is a kilogram meter per second squared. So that's going to equal the square root of kilogram meters over kilogram meters per second squared. These cancel out, seconds comes up, square root, and the unit is seconds. So that's your basics on periodic motion, right? What you need to recognize is the deep similarity of the processes underlying all these different kinds of periodic motion. And these formulas, they're simple enough to work with. You just need to be able to plug numbers in for that. So let's take that to work with today. And tomorrow we'll talk about a couple other ideas, more about natural frequency and resonance. So have a good day, and I'll look forward to seeing your work.